have faults, but not no faults in the same system.
Remember, those fault systems can be huge. So when you're up taking a close-up photo, you may have a thrust fault 10 kilometers away that contributed to that particular system. All right?
All right.
All right. Now, any questions from last time? In lab today? Yes, we have a exam in lab today.
Yes.
I think you'll enjoy that exam. It's going to be fun. Yes, sir.
Sorry, I'm a little skeptical of how much we'll enjoy the lab exam, but what are parasitic fold systems? What are
parasitic folds? We will get into that in a little bit more detail, but the quick answer, Tim, is that in general, when we take a layer of any kind, and here I'm treating it as a single layer, we generally try to simplify this, particularly in physical geology, into a single fold, so that we simply describe this, and in physical geology we'll say this is an anticline. But what happens in most systems is that they are not single layer, they are multi-layer, and you may have multiple scales of folding develop. And so it is not uncommon to see folds that are on a relatively larger scale and then see small scale folds develop inside those, so that these would be smaller scale folds superimposed inside of a larger scale fold. And so we can, and in fact, a lot of times, and this is probably way too much information, you see that sort of geometry. You have parasitic folds on top of parasitic folds on top of parasitic folds. I've seen them up in the Appalachian system where I work up to 5th order of smaller, just progressively smaller and smaller and smaller folds, where you're out in the field and you're going, no, it can't possibly continue like this, and then you go, okay, yeah, it does. You find folds of all these different sorts of scales. So we looked at, and we took an overview of folds this last class period. The takeaway from that is that we find folds on all scales. We find folds on the millimeter scale. We find folds that we can pass around in the classroom, and I brought a couple of other folds here. We find folds in different materials. For example, this is a piece of the Conococheague limestone. This was taken, okay. This was collected north of Front Royal, Virginia, right on the Shenandoah River. This is a Cambrian age limestone, and you see a beautiful, what appears to be a little anticline here, except the problem is that this is a rock fabric that has been folded, not rock layering, but an actual fabric that has been folded. So that is a type of crenulation. Here we have a beautiful fold. This was sent to me by a former student, Andrew Matson, that took his bachelor's here years ago, went to Caltech for his doctorate. He's now at Oxford University. And when he went to Caltech, Andrew collected this and sent it to me. This looks like a beautiful recumbent fold. And it is, but it isn't. This is a rhyolite. So this is a flow front in a rhyolite in that system. So folds occur on all scales. We find them in all materials. So we find folds in sedimentary rocks. We find folds in metamorphic rocks. We find folds in igneous rocks. If you drive around Tulsa, you can actually find folds in the interstate system during the heat of the summer as the system starts to buckle. If you look at the guardrails closely, you can see buckle folds within the guardrails as they begin to buckle, or if there has been an impact. We find them in all different types of materials, in geologically and in other materials. And we find them in all structural domains. So we find folds in thrust fault systems. They are integrally associated with thrust fault systems. We find them in strike-slip fault systems. We find them in normal fault systems. Any type of structural system, extension, shear, contraction will give folds. So folds are a very interesting type of behavior in a system. So we want to begin to understand a little bit about folds, how they form, how we might visualize them, how we might think about the way that folds interact with topographic surface so that we can actually begin to recognize folds out in the real world. Once we become proficient at recognizing folds on the real world, I hope that you get enamored with folds. I adore folds. Folds are fabulous. The only problem with folds is that they have a tendency to irritate other drivers. Because you'll find a fold, you'll slam on your brakes to take a closer look at it, and invariably there's someone behind you that doesn't appreciate the fold quite so much as you do. So if you get enamored of the folds, just drive carefully, slam on your brakes carefully so that you don't get really annoyed at some point in time. So what we want to try to do is first off, we want to try to understand the geometry. What is the geometry? How do we describe the geometry of folds? What are the geometric elements? How do we begin to visualize them? We want to understand a little bit about these parasitic folds, and we want to at least touch, and probably fairly gently, on how we might describe them mathematically. Because once we start thinking about these, then we get into the Fourier series domain, and then that gets a little bit higher level than we're really looking at. So the geometry, the geometric elements of a fold. And let's put that in quotation marks, because that is going to be independent of scale. Doesn't matter whether we're dealing with a large scale fold, a small scale fold. We're looking at certain geometric elements, and we're going to visualize a fold. And please keep in mind that this is simplistic. This is a very, very simplistic treatment of folds at this point. When we look at a fold, we typically visualize a fold as being periodic. We're repeating some pattern. And again, let's put that in quotes, because they need not be perfectly periodic. But this is our most simple beginning. And if we look at this, if we take one piece of this fold, what we're going to do is we're going to describe various parts of that particular fold in that system. Well, let's take a full circle. So there we have a full cycle. You can think of this right now. It would not be inappropriate to think of this as a sine curve or as a cosine curve. So that, I think that's the end of that one. In this particular case, what we can do is, as we come up, does anything change? The slope changes. Could we come up with any type of a descriptor that might allow us to further classify pieces of our fold?
Sinusoidal.
Sinusoidal. When you think about, let's go back to Calc 2. Calc 1 was, baby differentials, baby integrals. Calc 2, they got a little bit nastier, and they talked about trying to do some sort of functional analysis and visualization of some of the things that can happen. Could we come up with a descriptor that might allow us to understand the way that the fold is curving?
Like amplitude and frequency?
Yes, amplitude, frequency, curvature. So we can think of amplitude. Let's think in terms of wavelength, if you will allow. Throw in a little bit of physics too. Amplitude, wavelength, curvature. Now, the amplitude of a fold. What we're going to do is define the amplitude of the fold. We're going to choose a midpoint, and we need to find out how do we choose that particular midpoint. And the amplitude is simply how high that particular fold is from that midpoint line up or down. The wavelength in a system, that is how far we have to go. Now we're thinking in terms of distance, how far we have to go to repeat a full cycle. Now, in a complex fold set, we have to be aware that we might have a range of amplitudes. We might have a range of wavelengths in a particular fold. If we just looked at this one over here, we would have a descriptor for the larger scale fold and then for each of the smaller scale folds. Now, curvature. How do you define curvature in Comp 2? You take a fairly simplistic approach, and then there's a little bit more sophisticated approach.
The tangent of...
So we're looking at the rate of change of slope. So the way that we define curvature in a little bit more rigorous form is we're going to look here at the rate of change of slope over some small arc length. Over some small differential arc length. That gives us curvature. So that if we look at a few simplistic examples, if I have that is my curvature, and we're going to think very, very simplistically. In this case, let's always think in terms of absolute value of curvature. Is that a large curvature or a relatively small curvature compared to something like this? This has a relatively low curvature. This has a relatively sharp curvature in here. That would get to a relatively high number. What if we did something horrible like this? I can just see Dr. Pomerantz rolling her eyes. What would the curvature do there? Yeah, it's a straight line, so nothing, 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 and then boom! We go to infinity. And then back to nothing, nothing, nothing. And so curvature can be a relatively useful tool in these particular systems to help us begin to understand components of a fold. So if we look at the curvature of a system, let's say that we have a fold set that looks like this. Well, we have some intriguing domains in here. We have a domain in here where curvature is less than 1. So we can define a zone in here, and I'm thinking absolute value. I'm always thinking absolute value of curvature. We don't like to have negative folds. That's kind of like having negative friends on Facebook. We have absolute value of curvature is going to be less than 1 in that particular system. We have a domain in here where the curvature is going to be greater than 1. We have a domain right there, a point where our absolute value of curvature is a maximum. And again, absolute value. So that's where our fold is the tightest. That's also where we turn over in our system. We have points, I've marked them there and there, where curvature is exactly equal to 1 on our system. And we're going to give these names. This point here we're going to call our hinge of our fold. So we have a hinge there, we have a hinge there, where we have our greatest rate of change of slope in that system. These points here where curvature is 1, where we go through, actually I'm sorry, that goes through a 0, duh. When we go through that 0 point, that we're going to call an inflection point. These zones in here, this is what I'm going to call the hinge zone. And this part I'm going to call the limb of a fold. So we can give folds some descriptive terms just based on a definition of curvature. We can talk about our wavelength, we can talk about our amplitude. So we can have folds that have something like this. Would this be low amplitude or high amplitude? It's going to be a relatively high amplitude versus something that is very gentle and open like this. So we can define and describe folds based on these simple geometries. Now, if we look at our folds, we find some intriguing things going on with our folds that may be reflective. They may tell us something about the behavior of the material. Now, we're not yet ready to delve into mechanics of materials, but keep that thought in mind as we progress through the course, as we learn about stress, strain, and finally get into mechanics of materials, that a lot of times what we see in these fold systems is expressive of how the material was behaving. What flow law were we following at the time that the folding took place? Now, a few other things we want to note about folds, and we've drawn some. A lot of times we think of folds as these perfectly symmetric features. So if we take a mirror axis here, it looks the same on either side. That's a nice, perfect symmetric, and we tend to think that they're continuous and mundane forever and ever and ever. They don't change shape. Well, that's not reality. They can change shape dramatically. We can have asymmetric folds that look like this. And in this particular case, what will happen is that a lot of times in asymmetric folds, one limb is longer than the other. In this case, this limb is overturned. So if we filled in a layer here, like this, our Younging direction, if this is an anticline, would be downward. It would be up here, turn, go downward, come back, and the Younging direction that way. So that concept, so we go back to the second lecture, second discussion, and we can use the Younging direction to help us interpret what's going on in the folds. in these particular systems. So they can be symmetric, they can be asymmetric in this system, they can be nicely periodic, or they can be non-periodic. We can have folds that look very, very oddly, where we will have fold sets. If we have a nice periodic system, okay, there's a nice periodic fold. I've never seen anything like this in the field. It just doesn't exist. What we typically find is that the folds will take changes in geometry and do weird things like this, where it's not really repeating on that much. I put in some periodicity there. My bad. This one is starting to become non-periodic. The shapes are not persisting in our X dimension here. What we also find is that when we look at folds, we find several different two-dimensional shapes, and we're going to jump into three-dimensional shapes of these fold sets. What you probably have gotten in physical geology is folds acma. That looks something like this, where the thickness of the layer stays constant throughout. So in this case, that T thickness is constant throughout the fold. No changes in thickness. And you probably, if Dr. Cornell got into that, this would be called a parallel fold. This is an old classification. This is a classification from the 1950s, where we're looking at a constant layer thickness. As we play with this particular fold, we're going to find out that this particular fold has a few problems. Because if I take a parallel fold and I try to maintain constant thickness of layers, what happens? I'm starting to get into trouble here. The fold will sharpen with depth. And there will come a point where I can no longer draw the fold. And so the old classification of parallel leads us into some problems with how the fold system can behave. We know that fold systems are not just single layer, they're commonly multi-layer systems. And so how do we build folds in a multi-layer system? Well, if we go back to what we saw in physical geology, there's probably another style of fold where we're looking at something like this. And we can keep drawing this and drawing this and drawing this, where each successive shape is similar to the others, but you'll notice there's quite a bit of thickening here in the hinge zone of the fold. This is what we termed a similar fold, where thickness will vary. The limbs are a little bit thinner, the hinge zone is a little bit thicker. It apparently has material compressing, and this is the basis for some of the terms that we were using last time. We talked a little bit about flexural slip versus flexural flow folding. Well, if we imagine this, in order to have a fold that behaves like this, there needs to be layer parallel slip. It has to be like a deck of cards or an old phone book where you bend it and the layers, the pages can slide past one another. Then we can begin to accumulate this style of fold. Here, the layers are locked. They're not allowed to slip past one another. So instead, we're actually deforming the material in here. We're seeing deformation of material. And the original thought was that the material was flowing from the limbs into the hinge of the fold, which is not necessarily the case. But in this system, this would have been viewed as flexural flow. This would have been viewed as flexural slip, parallel, and similar. Now, these are end members, and I don't know, as you've gone through life, you've probably learned that it's not always this or that. There's a lot of variance in between. So in the 1970s, there was a very well-known, highly regarded geologist, structural geologist named John Ramsay, who was teaching at that time. He was at Imperial College of London. And John was trying to analyze folds, had a group of grad students, and one of the grad students was Peter Huddleston. And so he bought Peter a Pan Am pass, that you could do this at that time, where you could fly anywhere in the world off of a single airline ticket as long as you were generally going east or as long as you were generally going west. And his charge to Peter was, for your dissertation, you're going to visit every country you possibly can and measure every fold you find. What a dissertation. That sounds kind of wonderful. You know, just go travel, have fun, and oh, by the way, measure folds. And what Huddleston found was that there were actually quite a large range of fold geometries. And he looked at all of these different geometries, looked at some of the early work that Ramsay had done, and came up with a classification system that is termed the Dip-Isogen classification system. Bless you. And he found really 1A, 1B, 1C, 2, and 3. So he found 5 different general forms of folds, and he used the concept of the Dip-Isogen to classify. And we need to try to get into his head and understand what a Dip-Isogen is. In this construct, what I'm going to do is I'm going to draw a very general and gentle fold. Okay? And obviously not very pretty. So here, if this is our fold, we're going to look at this as our axial surface here. So this is a hinge surface that is cutting through the center part of the fold. We're going to look at a single layer, and then we're going to talk about arc tangents. Okay. And we're going to use some odd terms like the inner arc and the outer arc. Tangent. So now let's imagine that that's a zero line, zero dip. If we take a 10-degree dip, it will touch this arc in one place. So if I have a 10-degree dip line here, it becomes tangent at that point. So that is where that dip tangent, 10 degrees, touches the outer arc. If we come down and do that again, it touches here. So my dip isogen is this. That is my 10-degree dip isogen. The 10-degree dip isogen connects the points at which a specific dip angle becomes tangent to the inner arc and the outer arc. Okay? Are we good? So, what Huddleston found is that in looking at these, he found that here what happened is a couple of different things. If we fill this out, what we find is that these dip isogens are converging downward. Oops, I ran out of the In type 2, he found that the dip isogens were parallel. And in type 3, the dip isogens converged up. And so in looking at these geometries, he found a rather intriguing combination. He found some folds that look like that. That's kind of a, wow, how did that happen fold? He also noticed that the curvature of the outer arc was less than the curvature of the inner arc in this. He found folds that did this, where again the dip isogens converge downward, and the curvature of the outer arc was less than the curvature of the inner arc. And he had some folds, let's sharpen this curvature, where there was just the slightest amount of thickness change that it converged gently downward. But just a little bit of thickening in the hinge of the fold. In the type 2s, what he found was this geometry, which we called similar before. And in this one, we had some very intriguing systems where you have this. Where the curvature of the outer arc was greater than the curvature of the inner arc. So we go from curvature of the outer arc in this case is less than curvature of the inner arc. That's not Central Intelligence Agency, that is geology. Curvature of the outer arc, curvature of the inner arc. In this case, the curvature of the outer arc is equal to the curvature of the inner arc, and in this case, the curvature of the outer arc is greater than the curvature of the inner arc in that system. So we had converging downward dip isogens in here. This is strongly convergent to weakly convergent. Parallel dip isogens in here, divergent dip isogens in here, or convergent upwards, and where our folds changed geometry rather dramatically. So this is his change in the classification system. And he went on to realize that you could do a detailed Fourier analysis of these fold systems, and the Fourier analysis came up with similar types of classification, similar types of Rubik's clusters. in a system. So the dip-Isaac classification system can be very, very useful in trying to understand some of the basic geometries of the folds and in trying to understand, in some cases, how the folds form. Thicknesses will change across the fold. Folds are not always nicely periodic. They tend to vary rather dramatically. But let's extend our fold into 3 dimensions. Let's allow our folds to extend in and out of the board. When you do that, we can start having a little bit more fun. So let's say that we have a fold here. I'm going to extend that fold on out, projecting it into the board, so that we've been thinking about this system. Now we have a hinge line here and a hinge surface. And we can start playing with how do these behave in real world. And so this morning I spent hours and hours and hours building folds for you. So each of you gets a fold. And I even drew the hinge line on it. Took me forever. I've been up all night doing this for you guys. So we're going to work with every possible orientation that we can have for a fold. So we have our fold. Now, if you take this fold and do this, that's an anticline, right? So we can make an anticline, we can make a syncline, like this. So far so good? So, anticline, syncline. Now, what if our anticline, the hinge line, is no longer horizontal? We can make a plunging anticline. So instead of what we're going to call here upright horizontal, we have a plunging anticline. Can we have a vertical anticline? Of course. We just have the hinge line going straight down. That's a vertical anticline. Okay. This we're going to call upright horizontal.
No, I mean between like verticals and right.
Ah, good question. If we think, if we come back here, Angelina, and do this, which one of these is the older? So this is the oldest. So in an anticline, you have the older rocks in the middle. If I take a syncline, which one's the oldest? So this would be the youngest are in the center. And so we would have to look at the age relationships. So we've got upright horizontal, plunging, vertical. All right? So let's go back. Upright, that's inclined. That's an inclined fold. That's a recumbent fold. Okay? So let's run through. What are the characteristics of an upright horizontal fold? The hinge line is horizontal. The hinge surface is vertical. Okay? Plunging. The hinge line is plunging. The hinge surface is still vertical. Vertical. The hinge line is vertical. The hinge surface is vertical. Let's go back. Incline. The hinge line is horizontal. The hinge surface is dipping. Good? Recumbent. The hinge line is horizontal. The hinge surface is horizontal. Now we have two other things. Let's go back to here. We're going to now make an inclined plunging. The hinge line is plunging. The hinge surface is dipping. That's inclined plunging. Let's go back to vertical. And now we're going to rotate around the horizontal axis here. That is what we call a reclined fold. The hinge line is plunging. The hinge surface is dipping. Okay, I have a question for you. By the way, this is the perfect thing for a date if the date's not going well. You know, you've run out of things to talk about over the dinner table, whip out a fold. This is why I'm married, okay? Now, so we take this as vertical. She said yes. Take this as vertical 39 years ago. Take this as a vertical fold, rotate it. The hinge line is plunging. The hinge surface is dipping. By the way, Gail's a structural geologist, and so you should understand. Take this one, hinge line is dipping, hinge surface is plunging. Or hinge surface is dipping, hinge line is plunging. What's the difference? Well, if we think about the orientation of these surfaces, we have to think about something called the pitch of a surface, of a line in a surface. So let's go back to, let's look at our podium rather quickly. Here we have a surface. If we think about strike, remember the strike is a horizontal line in the plane. The dip is going to be the angle, the vertical angle, from the horizontal down to the plane. But if I put a separate line on here that is at an angle to my strike, the pitch is that angle inside the plane, in the plane itself. So in this case, the pitch is oblique. Okay? So let's go back. Let's get our fold back out. Don't lose this. They're incredibly valuable. If we do the vertical, let's go back to a vertical and tilt. What is the pitch of the hinge line in the hinge surface here? You can ask it. What's the pitch? It's 90 degrees. The pitch of the hinge line in the hinge surface in a reclined fold is 90. We come back, incline plunging. So, what's the pitch? Listen carefully. Okay. It's oblique. Less than, depending on how far, depending on the orientation of the fold. So, as a review, upright horizontal, plunging vertical. Inclined, recumbent. Incline plunging. and recline. Those are the different orientations of folds that we find in nature. Now, that begs the question, how do folds interact with the Earth's surface? And so we want to look at the concept, revisit. If you did this in physical geology, I do not know. Did you do block diagrams? Yeah, or for anything. Did you love block diagrams? So let's do block diagrams. So we're going to do a block. Here's a block of the Earth. We're going to do an anticline. Let's do an upright horizontal anticline, the easy one. Since I'm oldest, I get to pick the easiest. So we're going to do an upright horizontal. So my fold is going to look something like this. Okay? I'm going to label 1, 2, 3, 4, 5. This has to be 4, 5 there, 5 there. If I draw the axis of my fold, I would put it on the map surface and I would do that. Right? And if I were to put in some strike and dip symbols, I would put them like so. And as I come in, I would say, okay, that's 3. Oops. Did I miss number? This is going to be 4, 5, yes, 3. So that is an upright, horizontal anticline in my block diagram. Are we good? Well, let's do one more. Let's get rid of this stupid podium. Let's do an upright, horizontal, wrong color, syncline. Rachel, did you block diagrams in physical lab?
We have not known yet, we're still not.
Okay. You should.
Still.
So I'm going to put a syncline in here. I'm going to make it a little bit more complex. How would I number these features? Which is 1? Which is the oldest? So the oldest is in here. 1, 2, 3, 4, 5. So 5 up here is the youngest, is in the hinge zone of my syncline. Right? So this one is 3, 4. This one is 3 here, 2, 1. If I draw the axis, in this particular case, it would point in towards the center as a syncline, and I would put a strike and dip symbol, again pointing in towards the hinge of my syncline. So here's a challenge. On Friday, we're going to draw a plunging anticline and a plunging syncline. Except since I'm old, I'm going to feign senility and I will have forgotten how to do it. And so one of you brave people will have to draw a block diagram for a plunging anticline and a plunging syncline. And it'll probably be you, Angelina. For what this would look like, because we want to start visualizing how do these things look if they were cut by the surface. So keep this, take it on your date this weekend. Use it during an emergency.